Salutations and welcome to Space Time Continues. My name is Mary Louise Davey, and let's get going to space. Over the past few weeks, we've looked at robots taking over, doomsday scenarios, specifically climate change, and we've seen the trouble that the world's in that we have to look forward to. So this brings us to the cool part of space, the part where we leave the exosphere, and the many possibilities for our future. From methods of travel and all of the different sorts of spacecraft we, or maybe the aliens will have, could have, are being worked on now. Touch of awesome, right? So let's get started. And then we'll catch up with the launch a little later in the show. When we look at spacecraft, we need to understand their power systems. Power systems not only must be reliable, as one hopes. I mean, you're light years away from Earth. That means you're light years away from help. They need to operate in space, which means a hostile environment, an extreme environment. So, with the ever-increasing power demands of a more complex spacecraft, what does the future hold for their power? Technology? What do we have? Well, the Voyager space probe that was developed back in the 1970s. That technology, well, it launched 38 years ago, and it's still sending data from interstellar space. Its current destination is the star Sirius, 10 billion years from Earth. A side note, its journey will take 296,000 years to reach Sirius. So let's hope that some sort of human is still here at the time. But what I'm getting at is the technology. The Voyage probes can process 81,000 instructions every second, but your smartphone, it's more than 7,000 times faster. However, you have to plug it in or recharge it wirelessly, probably at least once a day. Whereas with a spacecraft, recharging's not really a possibility. So odds are it's 100 million years from the nearest outlet, and well, this means that instead a spacecraft must be able to either store or generate sufficient power to keep going for decades. I mean, decades at the least, millennia at the best. It turns out that that can be a very difficult thing to achieve. Sure, some onboard systems aren't active at all times, but others need to be on constantly, like life support, lighting, maybe the shield up in front that, blocks all the radiation, or perhaps lasers to blow apart the asteroids, whatever else you can think of. In the case of manned spaceflight, or even on a space station, you would need those kind of things, no? Dr. Rao Sarampudi is the Power Technology Program Manager for the Jet Propulsion Laboratory at the California Institute of Technology. And according to Sarampudi, you can count on 30% of the mass of a spacecraft being taken up by the following: power generation, energy storage, and power management, and distribution. You really have no choice. These are the systems that are crucial to your operation. So obviously, low mass, long life, as in the Voyager, and energy dense, meaning that they must produce a lot of energy in a relatively small volume. Reliability is key, but also backup systems, as space is not the place to be stuck with life support on the Fritz or other systems. Sounds kind of tough, right? Well, to understand the complexity of the systems, consider what you want out of it. I mean, it's not like your car. You can maintain it somewhat, but think about where you are, where you're going, how long you'll be traveling. These systems need to last for decades, millennia. So, per Sarampudi, the intended lifespan has to be long, for if something goes wrong, you cannot go there and fix it. He also says to go to Jupiter will take 5 to 7 years. To go to Pluto, more than 10 years. To leave our solar system will take 20 to 30 years. Operations needs to consider things such as varying temperatures. I mean, you might think you have to deal with much when it's a negative 150 Celsius. That's negative 253 Fahrenheit. That would be 1 minute. Next minute, you might have to deal with 360 degrees Celsius, and that's 860 degrees Fahrenheit. So that's kind of hot. So zero gravity, operating in a vacuum, radiation. Granted, if you were headed to the center of the solar system, you would have the advantage of an abundance of solar energy thanks to their photovoltaic solar panels. But what about other places? What about the places we want to go? We want to leave the solar system, right? One type of energy storage system to consider is nickel-hydrogen batteries. They can be recharged more than 50,000 times and have a lifespan of more than 15 years. So we're up to a good start, right? Well, commercial batteries do not work in space, and these batteries are sealed systems and can operate in a vacuum, and that's kind of important. So when you head away from the sun, solar radiation becomes more manageable. It's decreasing from about 1,374 watts per meter squared near Earth to 50 watts per meter squared near Jupiter. Negligible at Pluto, as it manages a minuscule 1 watt meter squared. So when you get out there, a spacecraft flying beyond the orbit of Jupiter, scientists look to atomic systems as a way of powering a spacecraft. Perhaps we need to look at how our robotic spacecrafts have been designed thus far and just change the scale. I mean, the most common type are the radioisotope thermoelectric generators, which were used on the Voyager, which is still working today, Cassini, the Curiosity rover. These are solid-state devices, which means they have no moving parts. They generate heat from radioactive decay of elements, such as plutonium, and have a typical lifespan of more than 30 years. But alas, to handle the added systems of a manned voyage, we're going to need a little bit more. We need to expand what we consider. It's likely that in the future, spaceship fuel would also be used to help power a settlement. Like once you get there, you know, like it powers you all the way to Mars, and then you use it to power your settlement on Mars. It's basic, right? Currently, solar cells are being developed to work in conditions where the light intensity and temperatures are low, making it better for solar operations, anywhere to on the moon or powered spacecraft that will be able to fly further away from the sun. At some point in the future, NASA will also be seeking to install a permanent manned base on Mars. As covered by my blog, their funding now puts the 2020's date in jeopardy, which say it isn't so, because I really want this to go on exactly when it's planned to be. I mean, in my lifetime, please, let's get somewhere. Let's get out in the solar system. Let's get out there. So these future power generation systems will need to be much bigger than the current ones. They need to generate enough energy so a longer mission, you may go out farther out to stars, to Alpha Centauri system, but then you may want to power your base, so you're going to need a lot of power for that too. It's likely that in the future, spaceship fuel would also be used to power a settlement. At some point in the future, NASA will be seeking to install a permanent manned base on Mars. As covered in my blog, their funding kind of puts the original date in jeopardy, which isn't to say that isn't going to happen, although I'm horribly upset because I really don't want any problems with this. And if you're going to ruin the Earth, can we please go to space? But nonetheless, these future power generation systems will need to be much bigger than current ones so that they can generate enough energy for a much longer mission. As far as resources go, starting on the moon would be to our advantage. I mean, do you want to go up through our atmosphere on Earth, or do you want to go off from the moon? It'd be much easier, no? Besides being an excellent jump point to the rest of the solar system or even the universe, the moon is rich in helium-3, among other things, and that's a rare element on Earth. I mean, not that it isn't here, but it's a rare element. Not to mention it's an ideal fuel source for nuclear fusion power. Unfortunately, fusion is not currently stable or reliable enough to be considered viable to power a spacecraft. A typical fusion reactor, say the tokamak, is usually housed in a building and the size of an aircraft hangar. And we don't want to mount that on a spacecraft. Perhaps a nuclear reactor? Electrically powered spacecraft and planned missions to land on the moon or Mars could certainly use that. And then the spacecraft's nuclear power generator would be the space colony's power station, no? Power plant. But apparently, we will not see nuclear-powered spacecraft for a few more years. Could be decades, really. Nuclear electric propulsion spacecraft are certainly being considered, but for longer missions. And in the future, the asteroid redirect mission requires large solar arrays to provide sufficient electric propulsion for the spacecraft to maneuver around an asteroid. At the moment, says Sarampudi, we are thinking of going with solar electric propulsion, but with nuclear electric propulsion in it. It will be cheaper. But as I said, it seems that won't be for some time. Launching to space is dangerous enough. The technology is not going to mature enough yet, says Sarampudi. We need to make sure that they are safe when you launch it. Testing is necessary to confirm that such power plants will be safe enough to withstand the pressures of spaceflight. Of course, if we were to use the moon as a launch point, it seems that would make it a bit safer. But that's my thought. So let's look at these futuristic plans that could make us our own space. So if you've been listening, astronomers recently identified an Earth-like alien planet around Proxima Centauri, the star close to our sun, the star closest to our sun anyway, making it the closest exoplanet found to date. Yeah, that's the star system, that's our neighbor, and it's a full, 4.2 light years away from us, away from Earth, and that's what, 25 trillion miles? So at such distances, will we ever visit this newfound planet? Unfortunately, the nearest stars would take tens of thousands of years to reach, using conventional spacecraft, such as the robotic probes now being used to explore the solar system. These spacecraft use a combination of chemical rockets, low-thrust ion drives, gravity-assisted trajectories, including so-called slingshot maneuvers around the sun or large planets that give them a big burst of speed. So we're going to need something a tad faster than that, at least. Maybe something like the giant Project Daedalus fusion rocket. Now, here are several ways that robots or even human explorers could visit the Proxima Centauri system or our cosmic neighbors elsewhere. Project Daedalus is just a concept design for an interstellar probe from the 1970s, and a group of technical specialists for the British Interplanetary Society designed it. So the target destination was Barnard Star, a red dwarf about 6 light years away, in some ways very similar to Proxima Centauri, where astronomers now report they have found signs of a habitable planet. When Project Daedalus was conceived, though, many astronomers thought it might be a gas planet that orbited Barnard Star, but to date, no planets have been found in that star system. So, the end result of the 5-year project was the Daedalus spacecraft, a 2-stage, 54,000-ton nuclear rocket that would boost a 4,000-ton robotic probe to around 12% of the speed of light. This would enable the probe to make the 6 light-year journey to Barnard Star in a mere 50 years. It would be powered by nuclear fusion using electron beams to detonate a stream of pellets of fuel, perhaps helium-3, which would be mined from the moon, where else? And while the engine would consume tens of thousands of tons of fuel to get to the spacecraft to its top speed in about 4 years, there wouldn't be any fuel left to slow it down. Minor problem. So it basically would do the 50-year journey, and it would result in a 70-hour flyby of the destination system. And then it'd just go off into interstellar space. And that's the end of it. But since Daedalus would be too large to lift from the Earth's surface, it would be built in orbit, meaning spacecraft like this couldn't be built without a capacity for construction in space. The science behind the Project Daedalus concept is better understood now than when the spacecraft was designed. Thanks to the immense cost and enormous technical challenges, it would likely be more than 100 years before something like Project Daedalus sets out for the stars. But there is Project Icarus. By the way, just for fun's sake, do you know where the name Daedalus came from? How about Icarus? Well, it's from Greek mythology. Daedalus was a skilled craftsman and an artist, and he was the father of Icarus. Now, it was it's a famous literary tale. It tells about Daedalus' wings. He manufactured these wings because basically he was shut up in a tower. And this was to prevent the knowledge of his labyrinth, which is a long story, from spreading to the public. So he wasn't allowed to leave Crete by sea. And of course, the king kept a strict watch on all the vessels, permitting none to sail without being carefully checked out. So since Minos controlled the land and sea routes, Daedalus set to work on fabricating a set of wings for him and for his son Icarus. He tied the feathers together from smallest to largest to form an increasing surface. He secured the feathers at their midpoints with string and at their bases with wax, and gave the whole thing a gentle curvature like the wings of a bird. When the work was done, the artist, waving his wings, found himself buoyed upward so he could lift himself up and hung suspended, poising himself on the beaten air. Perfect, right? He next equipped his son with the same thing, same set of wings to fly, and he taught his son, hey, this is how you want to do it, but do not fly too close to the sun or too low, because the sea foam would, well, soak the feathers and oh well. So, unfortunately, Icarus, well, he got a little full of himself when he got those wings on, and he was flying up and around and zooming around and doing, cartwheels in the air. And unfortunately, he flew too close to the sun, and he fell into the sea, and he drowned. His father cried bitterly, lamenting his own art and calling the land near the place where Icarus fell into the ocean Icaria, in memory of his child. Sometime later, the goddess Athena visited Daedalus and gave him wings and telling him to fly like a god. And so that's where Daedalus and Icarus, the names were taken from. Now back to space. The Project Daedalus concept from the 1970s are the inspiration for the Project Icarus, an ongoing joint project by the British Interplanetary System and the Icarus Stellar Organization, an international network of scientists, engineers, and enthusiasts who hope to develop the capabilities for interstellar spaceflight by the year 2100. The anticipated reach? Project Icarus is designed to reach any star within 22 light years that has potential of habitability. So that means that if a planet is confirmed around Proxima Centauri, then it would be a target destination. The idea was to update the Daedalus design with that of Project Icarus using new technologies and ideas. Among the refinements proposed are fusion rocket engines, which harness a different nuclear fuel which would be detonated by lasers instead of electron beams. A technology that could draw from recent advances in laser ignition fusion at the National Ignition Facility at Lawrence Livermore National Laboratory in California. Still, only a probe, the Icarus probe was also smaller than the 400-ton probe envisioned for Project Daedalus. Thanks to advances in electronic miniaturization and robotics and future nanotechnologies, which would mean the spacecraft would need to carry less fuel to reach its full speed. But maybe we wanted to fly. Perhaps we could be in space. It could be space pirates. We could utilize a light sail. No? Our best bet for interstellar travel is not to use a rocket at all. Light sails, which use the pressure of light to propel a payload, have been considered and used for interplanetary space probes, such as 2010 Japan's experimental Icarus spacecraft, which on December 8th in 2010, Icarus passed by Venus at about 80,000 kilometers, that's 50,200 miles, and completed the planned mission successfully before entering its extended operation phase, which it's always good to enter your extended operation phase. But while light sails driven by sunlight are already an effective way to explore the solar system, they can't cover interstellar distances in a reasonable amount of time. They'd be great for sending collected supplies from the moon and back to Earth, but maybe there's more that can be done. The answer is to use powerful lasers to push the light sail to very high speeds, with the bursts of light at the start of the journey, until the spacecraft is too far from the laser source to gain more thrust from the light beam. The huge lasers, which as an idea is somewhat similar to that of Yuri Milner and the Breakthrough Initiative. As you may recall, the project aims at a working prototype by 2036 and a final mission cost of about $10 billion, covered on earlier shows. Wouldn't be built on Earth or in orbit. Interstellar light sail spacecraft would not need to carry fuel for the journey, so the mass of the spacecraft could be kept small. The concepts behind the Breakthrough Starshot program have been studied by Philip Lubin, a professor of cosmology at the University of California, Santa Barbara, who says the biggest challenge remaining is to sufficiently powerful laser has to be created. Certainly this concept can be utilized in other plans as well. So how about the Bussard ramjet? Next to the Bussard ramjet, a concept proposed by physicist Robert Bussard back in 1960, the Bussard ramjet combines the high thrust of fusion rockets with the low fuel requirements of light sails. The first image is of the systems necessary, though the next is an image of displaying the full regalia of the Bussard ramjet. It would pick up its fuel by grabbing thin traces of gas and dust as it goes along, known as interstellar medium, using a vast funnel-shaped electromagnetic field that extends for thousands of miles in front of the spacecraft. Hydrogen from the interstellar medium would then be compressed and used as fuel for the fusion rocket and the rear of a spacecraft that would drive it forward. Acceleration is many of these sorts of propulsion dissipates greatly in space. You keep going though, so until something slows you down. The gravity pull of a nearby planet to an asteroid field, theoretically, in your spacecraft driven by a Bussard ramjet, you could accelerate forever, or at least as long as there's interstellar gas in your path to provide more thrust. And theoretically, you can even reach a high fraction of the speed of light. So, if it makes perfect sense that the Bussard ramjet was a favorite of sci-fi authors in both novels and short stories, what other things could you use? I mean, sci-fi predicts the future, right? Well, I used Vasimir engines in all my books, or most of my books anyway. So that's my preference. So there are other ways to go on. Alas, in sci-fi, there's no shortage of the interstellar medium, but in reality, around our solar system and the nearby stars, it's particularly thin. And there's likely not to be enough hydrogen there to fuel a Bussard ramjet. Now, shame, because it's a promising idea, right? Although there was a change of concept with the hope of taking a good idea and making it work. In order to get around this limitation, they would put fuel in different areas and through space so that when it came by, it could pick it up in those areas where space perhaps was not providing enough on its own. This collected matter, as a reaction mass to drive the spacecraft forward, is used in energy beamed to it by a laser with an interstellar runway, which would be used deposits of fuel positioned in advance of the spacecraft. It's a cool idea, but how do you feel about a concept that really kind of relies on what was placed out in advance of you being there? I don't like anything that relies on external pieces. But onward, what else do we have? Well, we have NASA's Evolutionary Xenon Thruster, the next project's 7-kilowatt ion thruster. So what am I talking about? The ion drive engine is a thruster where molecules of an unreacted fuel, such as xenon, are given a positive or negative charge, ionized, hence ion drive, and then accelerated by an electric field that is shot out the back, of course. Now, the thrust is incredibly low, about the equivalence of, well, that's it. So needless to say, an ion engine is slow to pick up speed. Still, over a long range, it can deliver 10 times as much thrust per kilogram of fuel as a chemical rocket. If you want an example, the Dawn space probe. Dawn reached the peak of its elliptical orbit on July 7th after cresting at almost 23,700 miles, that's 38,100 kilometers, above Ceres. The spacecraft began its slow fall back to lower altitudes. Today, the Dawn will descend from 23,240 miles to its minimum altitude on July 22nd. Used its ion drive to become the first spacecraft to enter and leave the orbits of multiple celestial bodies. But now let's look at the plasma propulsion engine. Take the ion drive and pump it up a notch. Instead of a non-reactive fuel, magnetic currents and an electrical potentials accelerate ions in plasma to generate thrust. It's an old idea, but it hasn't been fully utilized yet. Now, the coolest in my mind, and the one I selected in my Three Nación books, is the Vasimir engines. Considered to be the most powerful plasma rockets in the world, currently of course. The Vasimir, or Variable Specific Impulse Magnetoplasma Rocket, is currently in development by the Ad Astra Rocket Company. That's in Texas, I believe. Now, Ad Astra, if you recall, is headed by President and CEO and ex-astronaut Dr. Franklin Chang Diaz. The company's been working on Chang Diaz's concept of the Vasimir engines for ages. So far, they've completed testing of it on the ground here on Earth, but they had taken it, it wasn't fully closed up, but the engines, they passed. So then they went up to the ISS and they tested it up there. Now, there again, it wasn't the full thing, just the engines themselves, and it passed. Well, testing is still planned, the final testing, when they have everything, the whole package. It's going to be tested in a full vacuum on the moon. Pretty cool, right? I have very high hopes for it. What's next? What am I talking about next? Thermal fission, of course. A conventional fission reactor could heat a propellant to extremely high temperatures to generate thrust. No nuclear thermal rocket has flown as of yet, but the concept was certainly considered, more than considered, in the 1960s and 1970s, with several designs built and tested on the ground in the US. But that was then. The nuclear engine for the rocket vehicle application, that's NERVA, was deemed ready for integration into a spacecraft before the Nixon administration shelved the idea. They decided not to send people to Mars. Nixon was like, well, let's not send him to Mars. He decimated NASA's budget, so, oops. Nixon was considering going to Mars, and here we are some 40 years later, considering going to Mars. Progress. Which leads me to continuous fusion. Fusion-powered rockets effectively try to recreate the power of the sun by superheating fuel hundreds of millions of degrees until the atomic nuclei fuse and generate even more energy. A fusion rocket would be 100 times more efficient than the best chemical rocket. But continuous fusion engines working at achieving a net output from a fusion reactor, something that, well, several decades of research and a few $billion of funding have so far kind of failed. Turns out there are many forms of fusion engines. So next up, propulsed fusion. Believed to be the best achievable way to achieve fusion power, pulsed fusion used the controlled detonation of a miniature fusion bomb to power the spacecraft. A design that the University of Washington is attempting works by dropping a pellet of 2 hydrogen isotopes, surrounded by metal rings made of lithium, into a combustion chamber, and then a huge magnetic field slams the metal rings closed around the pellet, compressing the fuel to incredible pressures and leading to fusion. Here's the major problem. We can't test this option. You see, it would violate the nuclear test ban treaties and nuclear in space, a whole bunch of that. But I kind of believe that this is going to change. I mean, my thoughts are, if everybody's really around the same idea, thinking we got to get going, we can't get further unless we have nuclear, so we've got to do this in space, then if everybody, all these spacefaring nations, agree to drop some of them or be more careful with what we use, but we can use some, I see this happening. Here's an intriguing idea. Nano spacecraft. America tends to do things on a big scale, so this idea might come as a shock. But while most strategies for deep space transport involve building bigger rockets and more powerful engines, suppose we were to shrink the spacecraft instead. Well, in 2009, researchers at the University of Michigan tried to do just that. Develop a kind of nanoscale engine that could be patterned onto a silicon chip. It works a bit like a tiny particle accelerator, very high velocities, using simple electric fields between charged plates. Each chip could contain millions of tiny electric launchers. Now we get to antimatter. Presently, not much more than theoretical at best. Now, before you say, well, antimatter, does it even exist? Well, what do you think they've been gliding all these years at the Tevatron? Or even the LEP before it went away. And guess what the P in PET scan stands for? Positron emission tomography. So antimatter annihilations convert the entire mass of particles involved into energy. Following, of course, our good buddy Albert Einstein and his famous equation of E equals mc squared. A tremendous amount of energy can be produced extremely little mass, a kilogram of matter, annihilating with the same amount of antimatter, will release as much as the Tsar Bomba, the largest thermonuclear bomb ever built. So given this, you can easily understand why antimatter is being touted as, well, not to mention a future weapon, of course, but as the fuel, a source of fuel. Well, an antimatter-driven propulsion is one of the many hooks of science fiction, but a problem. And you knew if it was this good, there had to be one, right? Well, antimatter currently takes way too long to produce, and it's way too expensive. It can't be considered logical. You can't. CERN claims it has taken 100 million pounds to produce just 1/1,000,000th of a gram. And that's to make a gram of antimatter. That would take 100 billion years. So antimatter, it's made of antiparticles, which have the same mass as particles, but of ordinary but opposite spin and charge. Antimatter has the highest energy density of any known substance. If used as fuel, it could provide by far the most efficient propulsion system, with up to 40% of the fuel's mass being, the mass energy, being converted directly into thrust, compared with 1% of the next most efficient, which would be fusion, of course. But I digress. Let me get back to the space topic. In 2006, the NIAC, that's NASA's Institute for Advanced Concepts, funded a team tasked with designing an antimatter-powered spacecraft. They calculated just 10,000th of a gram of antimatter would be enough to send the spaceship to Mars in 45 days. Of course, the problem is getting that 10,000th of a gram of antimatter. The only way we create antimatter at present is in particle accelerators. But to give you an idea as to how much or how little we have created, if we were to use what we've created to date, it wouldn't be enough energy to boil a cup of tea. So what it comes down to, unless there's another way to create it, maybe it's found or developed or antimatter just is found running rampant somewhere, well, antimatter engines will likely always remain in the realm of science fiction. Let's look at more definite portions of the future, but first, let's go to space.
40秒。30秒。20秒。10、9、8、7、6、5、4、3、2、1，点火。起飞。
起飞 ，T0， 07时30分31秒409毫秒 ，T0， 07时30分31秒409毫秒。表团程序转弯，东风程序转弯。尾团光学跟踪正常，东风飞行正常。现在。
Now, granted, we've all heard of SpaceX and the rocket that will take hundreds of settlers up to Mars, but that rocket doesn't exist just yet. Elon Musk has called what will be the tallest spaceship ever built, about 3/4 as tall as the Washington Monument, a BFS, Big F spaceship, sitting atop a BFR, Big F rocket. Pretty cool, right? It'll have 28.7 million pounds of thrust at liftoff and places the spaceship up into orbit. That's 3 times as much thrust as a Saturn V, the largest rocket used in the Apollo mission. The rocket then returns to Earth, lands safely on a launch pad, grabs a fuel tank, brings it back up into orbit. You see, fueling the spaceship in multiple stages is crucial for bringing costs down, Musk explained. Since it's easier to lift lighter components out of Earth's gravity, it makes a lot of sense to load the spaceship into orbit with essentially the tanks dry, then use the booster and a tanker to refill it while it's in orbit, and maximize the payload of the spaceship, Musk said. Thing is, to me, it seems it would be easier, perhaps, if we did this in cislunar space. Perhaps the fuel was already waiting up there. Now, this plan isn't entirely far-fetched, and to be honest, I would be looking for more ways to find it incredulous if it weren't Elon Musk. And by that, I mean he has continued to do the near impossible or the really, really difficult in fewer attempts. Basically, he's a living, breathing Tony Stark of the Avengers. SpaceX has already used its 7-meter tall Falcon 9 rockets to launch objects into orbit. And the company has successfully landed 6 of those rockets back onto launch pads here on Earth. The concept is there. Falcon 9s are much smaller rockets, however. They generate 1.7 million pounds of thrust. So it remains to be seen if SpaceX can scale things up, which I'm sure they can. So let's look at the plan. We need a spaceship that will actually transport the future colonists to Mars. As you can see, we already have an image provided courtesy of SpaceX, and it is rather large. SpaceX's plan is like this. The ship will unfurl large wing-like solar arrays, which will then be able to generate 200 kilowatts. Next, it will travel at more than 60,000 miles per hour. That's 97,000 kilometers per hour, taking about 6 months to get there. SpaceX, unlike NASA, is going to use its rockets to lower itself gently onto the Martian surface. Descending through the atmosphere will allow temperatures to soar to 1700 Celsius, that's about 3000 Fahrenheit. And to all that, Musk finishes with and that is that, we're on Mars. He talks very wistfully and almost as if it were a fait accompli. And then he talks about many ships leaving at one time, so it would take hundreds of people instead of just 100. Perhaps not at first, but eventually bringing down the cost tremendously. The part I found intriguing is that eventually he says the ships would have all sorts of activities on them. I still have a totally different design in mind, which would possibly have on the ship malls and parks and give one space to enjoy life. A little different than, say, the Starship Enterprise, though kind of like it. But use something like the craft that Elon is suggesting, more to get up to the big craft. But that would take quite a bit of time to build. And mostly would it be built in space, or at least assembled in space. And that involves the technologies we've never really attempted before. But back to Musk and SpaceX and Mars. After a while, tens of thousands of flights, we would now have a self-sustaining society on Mars. Now, with Musk, goes into some detail about the ideas of terraforming with solar panels, geothermal power, as well as certain other areas. Maybe NASA could handle that area, and maybe he could handle some of the cool toys, or they could all work together. Actually, I wonder if Musk plans on using a landing similar to the robot, the one from Hawaii that builds a landing pad. That's so cool. Or I can't get my mind off of that. But anyway, why don't you stick around and watch this brief little film clip about SpaceX and about this really cool plan that Elon Musk has. I totally love it. And after that, well, I think I might slip in a new launch for you.
Apart, you'll know it's 15 seconds away from the liftoff. Again, not tracking any issues with the vehicle, everything pointing to go, where it should be about 20 seconds away from launch.
Vehicle to internal power.
Auto sequence initiated, vehicle now on internal power. The launch command has been issued. You can see the rocket engines firing. Power is going to start ramping up.
Engines, turbo pumps at flight speed. Engines at maximum.
Turbo pumps at flight speed and liftoff. Sergei Rosansky, Randy Bresnik, and Paolo Nespoli rocketing away from Baikonur and on their way to the International Space Station.
And liftoff.
You can see the very bright first stage engines cutting across the night sky there in Baikonur.
So join us next time when Space Time continues.
Houston, we've had a problem.